There is a massive difference between a script that calls an LLM and an actual AI system. Most developers are stuck building the former, long, fragile chains of prompts that break the moment an input changes. Today we stopped scripting interactions and start architecting systems. This is the linear chain trap. It's a standard chain. Agent A passes output to Agent B, who passes it to Agent C. It's a relay race. If Agent A hallucinates or makes a syntax error, Agent B has no way to reject it. The error propagates and the system crashes. There is no recovery mechanism because there is no state awareness. To fix this, we need coordination. Pattern 1 is the manager-worker model. Think of this like a lead developer assigning tickets. A central manager LLM breaks down a complex user goal into discrete subtasks. It maps these tasks to specialized worker agents who execute in parallel, and then the manager aggregates the results. This is crucial because it separates high-level planning from low-level execution, preventing the context window from getting cluttered. Pattern 2 is bidirectional collaboration, often called an argumentation loop. In a linear chain, you accept the first draft. In this system, we pair a generator agent with a critique agent. They enter a loop. The generator drafts code, the critique reviews it for bugs, and the generator fixes it. They don't stop until the critique approves or a maximum retry count is hit. This loop is the only reliable way to get production-grade code generation. But the gold standard for autonomous agents and what we're focusing on is supervisor replanning. This turns your linear script into a state machine. A supervisor agent doesn't just follow a list. It looks at the current state of the conversation and dynamically decides who should act next. If data is missing, then it routes to the researcher. If the data is there, then it switches to the coder. It plans step by step, adapting to failures in real time. This is exactly what we're building today. We aren't using a black box framework, we are using LangGraph. We will architect a supervisor router that manages a researcher and a Python coder. The supervisor will autonomously decide which agent to call until the user's request is fully satisfied. But theory is useless without execution. We need to define our state, build our nodes, and compile the graph. Let's build this system from scratch. Now it's time to get hands-on. Let's start by opening our terminal and creating a new folder called Supervisor System. Let's also move into it. The next step would be to create a new Python virtual environment. This will isolate our dependencies and avoid version conflicts. And after it has been created, we need to activate it. When you see the venv prefix in the beginning, that means it's active. Now we need to install a specific toolset for this architecture. We need LangChain for the general model wrappers, LangChain OpenAI to connect to GPT-4, and most importantly, LangGraph. Unlike standard chains, LangGraph allows us to build cyclic loops, which are required for multi-turn agent collaboration. Let's install those libraries. Once the dependencies have been installed, we need to create a new file called .env. Here, we will add our OpenAI API key here. We will load this into our environment variables dynamically later. Now we need to create our main.py file. We start by importing our types. We need annotated and typed to enforce strict typing on our state and operator to handle list merging. We also import load.env to pull in the API key that we just set. I just realized we need to install two more dependencies. Those will be the .env, which we will use to load our environment variables, and also Pydantic for using the correct base model. Here, we also need to update this import. Instead of LangChain core, we'll use Pydantic. In standard script, variables are local and temporary. In an autonomous system, we need a persistent shared memory. We define this as agent state. Pay close attention to the messages key. We use annotated combined with operator at. This is a reducer which tells LangGraph that when a worker returns a new message, not to override the entire history, but to append the new message to the existing list. Without this reducer, our agent would suffer from amnesia after every step. To keep our architecture scalable, we use the don't repeat yourself principle. Instead of writing a separate function for every single agent, we built a create agent node factory. In LangGraph, a node is simply a function that receives the current state and returns an update. Here we inject the specific system prompt, the persona, and combine it with the full message history from the state. We return a dictionary with the message's key. Because of the reducer we defined earlier, this return value gets safely merged into the global conversation stream. Now we instantiate our workforce using that factory. First, the researcher. We give it a prompt strictly focused on accurate data retrieval. Second, the coder. We explicitly tell it to output only code. Notice the separation of concerns here. The researcher doesn't try to write code, and the coder doesn't try to browse the web. They are specialized tools. The coordination logic shouldn't live inside these workers. It belongs in the supervisor. This is the core of the pattern, the supervisor node. Standard LLMs are chatty and unpredictable. We don't want a chat, we want a control flow decision. We achieve this using the structured output. We define a pedantic model called supervisor decision that forces the LLM to choose only from our valid workers or finish. By calling with structured output, we effectively turn the probabilistic LLM into a deterministic routing engine. It can no longer hallucinate a made-up step. It must adhere to our schema. We have our nodes. Now we need the edges. Let's initialize a state graph. We add our three nodes: supervisor, researcher, and coder. We set the entry point to the supervisor, ensuring every execution starts with a plan. We draw standard edges from the workers back to the supervisor. This creates the feedback loop. The supervisor delegates, the worker executes and reports back. Finally, the conditional edge. This replaces the hard-coded if-else statements of traditional programming. The graph checks the next key populated by the supervisor and dynamically routes traffic. If the LLM says finish, we hit the special end node, terminating the loop. The system is built. Now we need to run it. Let's add our final block of code. We invoke the app with a compound request, find the GDP of France for the last 3 years and write a Python script to plot it. This requires two distinct skills, analyzing and writing code. But before we run our code, there is a small final change that we need to do. Let's replace the GPT-4 Turbo with GPT-4o Mini. This change is needed because GPT-4 Turbo doesn't support structured output. Okay, now we are ready to run our application. Let's open our terminal and type python main.py. This will execute our script. Let's wait for it to finish. Here we can see the final output of our agent. Now it's time to test the code that it has outputted. First, we need to add matplotlib to our list of dependencies. For that, we need to run pip install matplotlib. Once it has installed, we come back and copy the outputted code. We create a new file called plot.py or anything you like and paste the newly generated code. Now let's see this in action. Let's run this code from VS Code this time and we'll get a visualization of the graph that our coding agent just created. You can see how beautiful it is. Let's recap what we just built. You moved from a brittle linear chain to a robust cyclic graph. You learned that state is what governs flow, not sequence, and you implemented a supervisor that allows for dynamic replanning. This is the foundation of modern agentic engineering. If you're ready to stop writing scripts and start architecting real AI systems, subscribe to ByteBuilder. We are building the future of software one pattern at a time.